Hello, welcome to Picture Me Coding with Eric Aker and Mike Mall. Mike, it's nice to see you. How you doing?
Doing okay. Back in California, which is nice.
It's nice to have you back in my state of California. Mike, one of the best things I've heard this year, I love it so much, is an album called Tundra Rock by a band called Slomos. I love this record.
I like it too. I was wondering how much of the fact that you like this band is that they're from Norway, but
It's not just that. They're from Bergen, Norway. Norge. They're from probably just a stone's throw away from where my great-great-grandparents came from. They're from Hardangerfjord. But the album's rad. It's like if you got Red Fang and The Sword to team up, and then you asked Ozzy Osbourne to come sing a little bit. It's so good. And there's songs on here that remind me of Caius. Like they're legitimately rad songs. It's so fun to listen to. The second song on the album is called Rice. It's like 6 minutes long. We were listening to it in the car the other day, and my son said, he's 10, by the way. He said, this is a perfect song.
I trust his instinct. I like the hints of Caius, big Caius fan. So I read somewhere that they call tundra rock their genre. It's not just the name of the album.
Exactly. Yeah. So it's not stoner doom, but it just hits you in the guts the way that the best stoner doom should. You know, there have been these, I don't know if they're silly or if they take themselves seriously, but there are people on the internet arguing whether or not stoner doom can exist if it doesn't come from the stoner doom region of California, Palm Desert. It sounds like a joke, but there are people who honestly make that argument. It doesn't count if it doesn't come out of the desert.
Is this one of those champagne versus sparkling wine debates, or?
Yeah, I thought people can't be serious in this conversation, but it sounded like there was a hint of seriousness. I don't think they were being facetious.
I have to admit that if I had a time machine and I could, go to one concert that was given, I'd love to go to one of those like impromptu concerts that Caius allegedly gave in the middle of the desert for their handful of Palm Desert fans. That would be fun. But I do believe that stoner doom can probably come out of places other than the high desert.
Yeah, that's just ridiculous. But Tundra Rock's my new favorite genre. I love this record. Slomosa Tundra Rock. They're from Bergen, Norge. What do you got, Mike?
So, forewarn you that my recommendation for this week is slightly on the sad side. So, it's this album that came out earlier this year by a rapper who goes by the name of Ka. The album's named "The Thief Next to Jesus." It's very distinctive. One of my kids recommended me this guy about, I think around 2016. He had this album out that was about samurais. It wasn't really about samurais, but it kind of used the theme of samurais to talk about other things related to his life. And he's put out a string of really interesting albums. It's not the kind of rap that you play at parties. It's very introspective and the kind of minimalist, but sort of high art. Anyway, the sad part is that he died about a week ago now, pretty young. I think he was 52. He had this really interesting life. He lived in this part of Brooklyn called Brownsville, I think. His real name was Kasim Ryan. And apparently he tried to be a musician early in life, and it didn't quite work out. And so he joined the fire department, and he was supposedly like one of the first responders at 9/11, and he rose to be like a captain in the New York Fire Department and stuff like that. And then kind of later in his life, one of the guys from Wu-Tang heard some stuff that he had done and invited him to be on a track, and that kind of restarted his career. And so he put out like something like 11 or 12 albums after that, all of which were pretty critically acclaimed.
Wow.
Yeah. Anyway, this most recent one is it's an interesting album. I really like it. It kind of explores the relationship between religions, Christianity specifically, and the Black community, and how that's been sort of a mixed blessing over the years, and lots of really interesting stuff. And a lot of the samples and music in the background is kind of like gospel music, spiritual music. Anyway, very interesting to listen to. It's one of those things you kind of have to focus in on and listen closely to his rhymes because they're very subtle, and he's not one of those guys who's going to make you get up and dance.
All right. Mike, we wanted to talk about something that's pretty technical and esoteric this week. And when I say we, I think I mean more you, and I just wanted to try to see if I could catch up. The topic is content addressable memory. I'd never heard of this. You brought it up, and I was like, is that a thing I should have heard of? This is a response I sometimes have in topics in our field. Should I have heard of this? Content addressable memory? But it's not just a random topic out of nowhere. Why do you want to talk about this?
So there's kind of two reasons. As you sort of know, I've been kind of looking at hardware lately. So very early part of my computing career, I was kind of interested in hardware, and lately I've been investigating it again. Sort of trying to figure out how my computer works and how servers work and so forth. And so I've been looking at various sources. One of which is this book I bought a while back called "The Essentials of Computer Architecture" by a guy named Douglas Comer. And so I've been reading through that, bit by bit. And
Is that like a textbook?
yeah, it's like a textbook. I think it's, designed for sort of like an undergraduate course in computer architecture. And it's
Mm-hmm.
been updated a couple of times. So it's got stuff in it that's pretty up to date. It doesn't talk about any particular processor, but it does, talk about things that are generally true of most modern CPUs and memories and so forth.
Mm-hmm.
And there's a chapter on memory, and there's one section in there on something that called content addressable memory. And I might have heard the term at some point during my career, but really I never looked into it too much. And so, the idea is basically what it sounds like, in that instead of addressing memory through some arbitrary location in the memory, you're using all or part of a piece of data to address memory.
The
And
content itself tells you where it's located in memory.
yeah, so as a programmer, it sounds a little bit like a hash map. So you've got this key value, and the key value gets you to a piece of data that is related to that key value.
Mm-hmm.
But the
Mm-hmm.
idea of doing it, in hardware, is to make it super, super fast. I have this one quote that I got out of a paper that talks about the hardware of content addressable memory. And it says a content addressable memory, or CAM, compares input search data against a table of stored data and returns the address of the matching data. CAMs have a single clock cycle throughput, making them faster than other hardware and software based search systems.
Jeez, that's fast.
Yeah, yeah. So, obviously that's a very special use case, but there are some situations where apparently that being able to get to a piece of memory in that way is useful.
Mm-hmm. Searching for the memory. I've got the content, and I just want to locate it based on the content itself. It's a little bit of a
Yeah,
head scratcher, though, isn't it? Because you almost have to imagine there's some schema, like you mentioned hash maps. Okay, maybe I can hash a piece of the content of what you're searching for. Does that make sense? It almost, they're like, when I try to hold this idea in my head, it feels like, well, doesn't it have to be really big? Like how quickly can you locate some data based on some piece of the data? What's the scheme that we use to search there, I guess?
I think the key is usually, something like a single word of data. So, something that is like the word size of the computer or the memory bus or whatever. The idea is that you, instead of searching for that word in an array or looking through it for it in a hash map, you have this piece of hardware, and you apply that word to this content addressable memory, and it essentially immediately returns you the address of the thing that you're looking for. And like here in this quote, it says it does so in a single clock cycle, so obviously very fast. Where you need that kind of speed is, I guess, another question.
Does anybody use these things?
They do. So there seem to be at least a couple of pretty common use cases for them. When you look them up, you'll find that a lot of times they are used in networking devices,
Mm,
things like switches and routers.
okay. Yeah, that makes sense.
So yeah, I mean, it does make sense. You've got a packet coming in, and it's got some destination address, and to forward it on to the right place, you need some information about what port to use or whatever. So
And
you
you want
can
to
use
retrieve that as
you
fast as possible.
right, yeah, you want to be able to using the destination address, you want to be able to retrieve that information as fast as possible and send it on, just to make your network latency as small as possible. Um, I think they are also, from what I've read, they may in some cases be used in CPU caches. So
Hmm.
in a CPU cache like L1 or L2 cache, the 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 internal circuitry is like looking up a memory address to see if it's already in the cache, and if it's not, then it loads stuff from the memory into the
Hmm.
cache. And I
Hmm.
I, I gather that there's some cases where they use this type of content addressable memory for that lookup.
So what I'm getting a little bit confused as to whether or not is this an obscure thing or is it just all over the place? Would it be ubiquitous? Would it be like I've got a MacBook Pro here. Is this a scheme that's used in there somewhere and it's just all over the place? We don't know about it, or is it more these niche areas, niche network, not necessarily networking, not necessarily niche, but specific types of hardware?
I don't know about the MacBook Pros. I should, because I have one and I've investigated its hardware a lot. But I think the sort of killer application for these things seems to be networking hardware,
Okay,
um,
all right, all right.
routers and switches and intrusion detection devices and things like that.
So is it related to software? Can I use this thing in my code? I don't care about
um,
hardware, Mike. Sorry.
yeah, I mean, you probably would not have occasion to use this technology directly in software that you're writing, unless you're doing embedded programming on a network
Right.
device or something like that.
I'd have to build a
Um,
system, right, in order to take advantage of this.
right. So the reason why I thought this was an interesting topic is not just because of this hardware connection. I think the hardware connection is interesting, and I was kind of both surprised and intrigued by this hardware. But
Well, actually, sorry. Can we just pause real quick? So this idea's been around a long time, probably, right?
yes, as near as I can tell, the first notion of this goes back actually to the 1950s.
Oh,
Um,
wow. Okay.
yeah, there was a guy who kind of had this idea of being able to use a word of data to be able to look up related things. This idea is also sometimes called an associative memory.
Hmm.
Like in Python or other languages, we sometimes call a hash map an associative array or something like that.
Yeah, it does sound like a hash map. It also potentially sounds like you might use like compression algorithms or something to look for patterns and then be able to relocate. This is just guesses. I don't really know. So it's been around since the 50s.
Yeah, it's been around since the 50s and been refined in various ways since then. So, however, if that were the only context in which this term was used, this would probably be like a very short episode.
Oh, nice. We can go home. I'll just go
Yeah,
back to drinking my coffee, sit on the couch,
yeah,
read my book.
yeah. So we're basically done here.
Oh,
Shortest,
okay.
shortest
Sorry,
episode ever.
guys, listeners.
Um,
Here's a boring hardware topic for you to listen to us ramble about. You're saying
um,
no, no, no. There's another context that this is important in.
yeah. So something weird and confusing happened related to this topic that I would not have anticipated. And that weird thing was that Geoffrey Hinton won the Nobel Prize for physics.
Oh, I was confused about that, and I still don't really get it.
Yeah, I
Jeffrey
had this.
Hinton. Maybe not everybody knows who he is. Tell us who he is.
So Geoffrey Hinton, he's a computer scientist. He's best known for being one of the people who sort of initiated and popularized the current deep learning, the world of deep learning. A couple of years ago, he and Jan LeCun and Ben Gio, is that his name?
Hmm.
Won the Turing Prize for the work they had done on neural networks and deep learning. So he's pretty well known as as a computer scientist,
Mm-hmm.
very prominent, very famous. He's also one of the AI people who's kind of like a AI doomsayer type.
Yeah. There was a
Uh,
really wonderful portrait of him in the New Yorker. I think it came out last year, 2023. Great article. Very fun to read.
yeah, interesting guy.
Lives in Canada.
Yeah, I think he's University of Toronto, maybe. Um,
Mm-hmm.
anyway, so yeah, he won the Nobel Prize in physics, and
For
uh,
physics.
yeah, so there. Just to address that a little bit, there were two Nobel prizes in this cycle that were related to machine learning.
Mm-hmm.
One, I believe, was the chemistry prize, or maybe the
Mm-hmm.
medicine prize that went to
I think it's
Alpha.
chemistry.
Yeah,
Yeah.
it went to the AlphaFold, and which I think was totally made total sense.
I will take your word for it. I've never studied chemistry. AlphaFold, folding proteins. Sure. Okay, cool. I
Yeah,
believe
well,
it.
just for context, I in the early part of my career, I worked with a group that did X-ray crystallography on proteins.
Mm-hmm.
And so, for instance, there was a person in that group who spent his entire PhD, 5 or 6 years, figuring out the 3D structure of one protein.
One protein, right. Exactly, right.
And so the fact that AlphaFold can predict or determine the structure of proteins for
Plural.
many proteins
Yeah.
is just practically miraculous. And so totally understand that Nobel Prize.
But wait. So I was like, I don't understand. For physics, this AI thing. So the Nobel announcement, and we'll give you a link to it, it actually reads, quote, they trained artificial neural networks using physics. And I was like, what? What? They trained on obviously not my field. I don't understand it. But that's a confusing sentence, right? I mean, you could say to me, they trained artificial neural networks using electricity, and I'd be like, okay.
Yeah,
I
yeah.
mean,
I
sometimes I wonder with the Nobels, like they don't have a computer science Nobel, so they have to maybe cram. They want to award the originators of AI in there, so they have to cram it into physics. I mean, similarly, like they gave Bob Dylan a literature one. That's a freaking travesty. They're never going to have a Nobel Prize of podcasting. So if we want to win that,
yeah.
we're going to have to try to go for the literature one, Mike.
Well, I would not rule out the possibility of a future Nobel Prize for podcasting, and
Okay, so maybe there's a
I
hope for
I
us.
think we would probably be right at the top of the list.
Wait. Let me read more from the announcement because I tried to unpack. I tried to understand it, and again, not my field. I can't judge. I'm just kind of like, what? Here's what the Nobel announcement says. This year's two Nobel laureates in physics have used tools from physics to develop methods that are the foundation of today's powerful machine learning. John Hopfield created an associative memory that can store and reconstruct images and other types of patterns and data. Geoffrey Hinton invented a method that can autonomously find properties in data and so perform tasks such as identifying specific elements in pictures. Now, you tell me, are these tools from physics?
Um, so I find this description to be a little bit vague and
Well, that
not
validates my
particular
confusion. I'm still confused.
not particularly helpful. So I had kind of the same reaction when I heard about this prize, which was, okay, are they just deep learning has probably been useful to physics? Are they just sort of shoehorning these guys into the physics prize because people have been using deep learning to get interesting results from their pictures of the cosmos or
Hmm.
their their particle physics data or whatever. So anyway, I was confused and I went to read about it. And, the first thing I noticed was that he shared the prize with John J. Hopfield or J. J. Hopfield.
Hmm. Hmm.
And I thought, okay, I am not totally sure who that is. So I'm going to go look into it. And he was recognized for what are now called Hopfield networks.
Mm.
And so at first I didn't realize that these things had any connection to each other. I just thought, okay, these are two guys that contributed to machine learning, so they just threw them in together the same prize.
Oh, okay.
Um,
They don't even know each other.
Well, yeah, I didn't know that they were in any way related. I remember like years ago they gave a prize for computational chemistry. So doing simulations of various types of molecules, and they gave the prize to multiple people who were prominent in the field but didn't necessarily collaborate. So
Hmm. Hmm. Some
anyway,
of them potentially even enemies in the same room together,
yeah,
accepting their Nobel.
very likely one is the nemesis of the other.
So we've
Uh,
got John J. Hopfield for Hopfield Networks, and we've got Jeffrey Hinton, the Boltzmann machine, which is really the root of what we use and what we think of as neural networks today. But there are
right.
other
So
types
I
of neural networks, right?
So I decided I'm going to go look at what John Hopfield did. He's specifically called out for these Hopfield networks.
Is he in?
Um,
Is his field computer science, or is his field like legitimately physics?
so I believe kind of in the middle there. So I think he was a computational neuroscientist or something like that.
Hmm.
I started looking at his 1982 paper, which is kind of what the basis of what's called the Hopfield network now, and for which he was awarded the prize. There is a line in the abstract that says, the physical meaning of content addressable memory is described by an appropriate phase space flow of the state of a system.
Oh, okay,
So,
yeah.
so I,
Wait. What's the paper called? What's the paper called? Did you give us a title?
so the paper, this is from 1982. The paper is called Neural Networks and Physical Systems with Emergent Collective Computational Abilities.
Okay, can we go back a little bit because these guys didn't invent neural networks. The concept existed before Hopfield and before Hinton, right?
It did, yeah. It's kind of hard to put a finger on exactly where it started, but there were some guys who worked at I think they were at the University of Chicago originally, and one of them ended up at MIT. So there was these two guys who I think I originally met at University of Chicago named McCulloch and Pitts,
Hmm.
and they they worked on what became called the perceptron. There was another guy, I think his name was Frank Rosenblatt, who worked with them, who kind of is credited with creating what's called the perceptron algorithm. But the perceptron was kind of like this very basic neural system that could do binary classification.
Hmm.
So, you could present it with examples of something, and if certain conditions were met, it would work as a binary classifier of other examples of that thing. It wasn't super sophisticated, but it had this sort of neural architecture, and it would work as a classifier. In the late 60s, early 70s, Marvin Minsky and Seymour Papert put out this book called Perceptrons, which talked about this technology. And they basically showed that the perceptron, as McCulloch and Pitts and Rosenblatt had envisioned it, didn't work that well. It failed on a lot of classification problems. So that book kind of famously halted research on neural systems for a while. But
Hmm.
obviously, people were still kind of thinking about it through the 70s and 80s.
Yeah,
Um,
the New Yorker piece on Hinton was talking about that. Like there was a lot of discouragement about these ideas, and Hinton just kept pushing and pushing and pushing on them.
yeah, and there was kind of a renewed interest in the 80s and early 90s. I remember there being when I was at the Supercomputer Center, there was a sort of a conference around neural networks, and a couple of journals spun up about neural networks, and then I guess it sort of went into hibernation again for another 20 years. But
So I kind of want to go back to this Hopfield thing because I got so lost trying to understand the Hopfield contribution. So Hopfield has this contribution to neural networks. The concept is now called the Hopfield network, and Hinton cited this. He used this when he was describing his concept of the Boltzmann machine or the neural networks that became really popularized later
right,
on. And I
right.
got
So
I
that
got so lost with the Hopfield network.
that's the connection between Hopfield and Hinton, is that when Hinton went on to talk about what's now called the Boltzmann, well, I guess it was then called the Boltzmann machine too. He was using a method similar to what the Hopfield network was using, except he added some. um, like a stochastic element to it, which is where the Boltzmann part came in.
Okay,
But
all right.
I
Wait.
think
I'm not ready for randomness yet. Can we go back? So you read a little bit of a chunk of the abstract from the Hopfield paper from 1982,
yeah,
and that brought us back to this content addressable memory, this bizarre hardware thing. How much of a how much are we going to be able to try to describe? How much are you going to be able to help me understand what in the world a Hopfield network is and does, and how content addressable memory is a part of that?
that's a good question. Um, so what he was trying, I don't know if this was his initial objective or if it's just something that fell out of the work that he was doing, but so he talks in the abstract and early in the paper about how this neural network that he has devised can be used as a content addressable memory. And he specifically talks about how you could store, say, the description of a reference to a paper, and then later you could go back and find that reference again in this content addressable memory just by using some subpart of that reference.
Hmm. And that strikes a bell with how we use these, LLMs or other neural networks today.
Yeah, so it's a different use case and a different technique than what is being used in the hardware CAMs, but I was just very intrigued by the fact that we have this same term in two pretty different realms.
Hmm.
He does talk about the possibility of turning these into hardware and using them as true content addressable memories that can tolerate a partial description of the data you're looking for, that can tolerate errors in the description that you're looking for.
Hmm. Hmm.
But essentially, what he built was he built a neural network. So it's a connection. It's a collection of nodes, and they're all interconnected, or at least all potentially interconnected. And each neuron, let's say, can have the output either 0 or 1 in his paper. So if you have a collection of these neurons, you can, you can have a binary state. So, say if you have 30 of these neurons, you can have 30 bits and you can have some state, which is 30 bits. And so what he found was that you could take a certain number of states and you could sort of encode them in this network. In other words, you could build this matrix of weights between the neurons, and then you could go back at some point in time and give part of that state to the network again, and it would return to you one of the things that you had stored in it.
Oh,
Um,
that
so
sounds interesting. Okay, I think I'm kind of dimly grasping. Sounds a little magical, to be honest.
yeah, it is a little magical, and so there's kind of, to me, there's kind of two interesting ideas in here. One is that um, to an extent you can store states in a network. I that in of itself is an interesting idea to me and sort of mildly magical.
Hmm.
Um, the other,
Multiple states, not just a single fixed state, because you can use it to recall, kind of.
right, exactly. So there's kind of a limit, and he talks about this in the paper of I think he determines that something like you can store you can reliably store a number of states which is about 15% of the number of neurons. So if you've got 30 neurons, you can get perfect recall on about 5 states.
Hmm.
If you've got 100 neurons, you could get recall in 15 states.
Okay.
So just
And this is like single layer, right? Because neural networks have multiple layers of perceptrons
yeah,
after
this
that.
is this doesn't this has one layer, but since they are the neurons are all interconnected, and there's sort of the weight between neuron I and neuron J is the same as the weight between neuron J and neuron I,
Right.
and
Okay. Symmetrical. Okay.
so this is kind of what I think would now be called a recurrent neural network, a simple version of that, because it's not, the perceptron was a strictly forward thing. If there were like now we have these things called multi-layer perceptrons, but the data only flows from one layer to the next layer. It never flows from one of the forward layers back to the
It never goes back, right?
earlier layers. Yeah, so you could store states in this network, and then the other kind of interesting idea in here is that in this network, there's sort of a dynamics to this network. So if you present it with an input that's not one of the stored inputs, it will sort of equilibrate into one of the stored states, which is
Oh, I don't
where
really follow
where
that. That's there's this like energy minimization that I kept reading about, and I completely did not understand it.
right. So the stored states sort of correspond to the minimum energies, local minima in the energy surface of this network. And so when you give it a partial state, the network will eventually evolve to one of those local minima, which is
Hmm.
one of the states that you're trying to store, or
We're trying to recall.
what you're trying to recall because you have stored. And anyway, I just find that idea interesting as well.
I think I would probably find it interesting if I could grasp it.
So one of the connections to physics here is this Hopfield network is similar to what in statistical physics is called the Ising model. So there's this person named Ising who came up with this statistical physics model of basically magnetic spins. He devised this model where you have magnetic spins arranged in a lattice, and the adjacent lattices can affect each other, and it will make the spins go up or down. And they discovered that you could do interesting research on phase transition and these Ising models. Icing as in ISING,
Yeah,
not like
it's a
cake
name,
icing.
not like frosting.
Right. Yeah. So anyway, the point being that, this is both something that's been useful in physics, but also has this connection back to statistical physics. So
Hmm.
I took that as a sign that, giving these people the physics Nobel wasn't as weird as I thought it was in the original look. So
Hmm. Okay. All right. So Hopfield networks, you've got a single layer of neurons. They're all connected to each other. You can store various states, not just single states. You can give it like a prompt or a piece of state. Prompt is maybe pushing it a little bit too far here. You can give it a piece of your state and it will recall through some kind of magical way the whole state. How did I do there? Is that kind of a summary, a rough summary?
yeah, that's pretty good. I found a blog post where they store like pictures of Simpsons characters in a Hopfield network,
Hmm.
and then they take like say half of one of those images and apply it to the Hopfield network, and they get back the original, the full original picture.
But it's not
Um,
like stable diffusion where you've got like the blurred image and it like blurs it down or it understands the edges. It's not like that. You're taking a real piece of the content
right.
without
Yeah.
modification and feeding it in, and it's producing the whole content.
Yeah, and it could be something with a little bit of noise in it, so it's not a
Okay.
exact copy of a piece, but
Doesn't have to be perfect. It can approximate,
yeah,
kind of.
sometimes it will find the wrong thing. So if you give it a pattern that's not close enough to one of the local minima, it may retrieve the wrong thing. There's some analysis in Hopfield's paper about how if you store more and more things in the network, you'll get more and more errors as you try to retrieve things.
Oh, that's similar to this AI overview I saw posted online the other day, and it was somebody was asking, "What's the difference between sauces and dressings?" And the answer was, "Well, sauces add flavor and texture to dishes, while dressings are used to protect wounds." And then the definition for sauce was add flavor, texture, visual appeal. Sauces can add contrasting or complementary flavors to a plate. For example, tomato sauce is a common base for Mexican salsas. And dressings are used to protect wounds and prevent infection while also allowing healing. The dressing should be large enough to completely cover the wound. A standard serving size for salad dressing, 2 tablespoons.
Interesting. It reminds me a little bit of the is a hot dog a sandwich argument, but
Okay, so we didn't really get to Hinton. I think I kind of am almost on the road to understanding this Hopfield network. I like the idea. I like how you described it as it's got states, and you can give it a piece of the content, and it will return one of its states. And it does sound kind of like how you started with content addressable memory. Okay, I think I could kind of grasp how these concepts are related. But then Hinton comes along, and what is he going to do with these ideas?
So he comes up with this idea that is called the Boltzmann machine, and so one of the features of the Hopfield network is that it has this sort of has these sort of stable local minima. The dynamics of that network are going to make it settle into one of these local minima, and that's actually what you want. And so Hinton's innovation on that was, well, I want to do certain types of problems, but I don't want it to settle into a local minimum. I want it to try to find the global minimum, or explore more of the phase space. And so,
And so, like, if I settled into if I'm predicting text, it might just the local minimum might be, well, E is the most common letter, so I'm just going to give you 4 billion E's now. Is that kind of an example of that?
yeah, that's fair. So he wasn't really trying to initially wasn't really trying to do machine learning. He was the original purpose of this, I think, was more or less just doing computation, solving constrained optimization problems. I'm speculating a little bit here because I have not read the papers in depth. I've read them a little bit, but what I think is happening is he's adding a little bit of randomness or stochastic aspect to the Hopfield network.
Hmm.
This I've done some work in the past that was similar to this. It was for a different purpose. It was for actual optimization of physical systems. But for instance, there's this idea called simulated annealing that comes up in Monte Carlo simulations occasionally. And the idea is that if you're in a particular configuration and you want to change that configuration to see if the new configuration is higher or lower energy, you can sort of randomly choose something from from the distribution of possible cases.
You can
And
guess. You could say, let's try this new guess. This is a pretty good answer, but let's guess a new one and see how it compares.
right, yeah. And so in certain types of Monte Carlo simulations, you use the Boltzmann distribution. And the interesting part about the Boltzmann distribution is that it has a temperature parameter.
Hmm.
So in a real physical system, if you increase the temperature, you can jump from one configuration to another configuration more simply because the energy barrier that you have to jump to get to that new configuration is reduced. And so the idea behind simulated annealing is that you sort of raise the temperature a little bit and try to find a new minimum to settle into, in the hopes that
Hmm.
you kind of try to find the lowest global energy minimum, and then you slowly reduce the temperature. They call it simulated annealing because it's similar to the process that you use for annealing metal, where they heat it up in a forge and then they cool it down slowly so that it stays homogeneous and strong.
Hmm. What about this? What if I'm looking for like a one of those cat cafes where you can go and pet cats and drink teas? And I've got like an 8 block radius I can look in, and so I just sort of randomly throw a dart at a big city, and I look in that 8 block radius and I don't hear it, so I just find it. So I just kind of randomly jump to some other part of the city. That's how I always thought of that kind of Monte Carlo thing.
Um, yeah, I mean that's essentially what you're doing. The idea though here is that you want to restrict that jumping to a statistical distribution that makes some physical sense.
Yeah, right. I'm not just randomly jumping to some random spot in the suburbs. I got to jump to places where there are likely to be cat cafes.
Well, and you have to make a jump that makes physical sense.
Oh, I
So,
can't just jump out into space and then pick a new spot.
yeah, I mean, if you were literally doing, if you were doing a search and rescue for a cat, then you could probably jump to any part of the city that you wanted to.
Mm.
But if you're modeling a physical system or a system that has certain types of constraints, then you can't randomly jump to any part of the phase space, or it makes less sense to jump to a random part of the phase space because
Okay, I think I
the
get it.
real
Yeah,
the,
because
the the real physical system wouldn't do that.
Right, physical properties wouldn't allow that, right? Okay, all right, all right. So we're still on this Boltzmann machine idea. We've got some randomness. You start talking about Monte Carlo. We can kind of use temperature to jump around, and then we're no longer just stuck with the minima that the Hopfield network would produce. That's sort of I'm trying to state back to you what you're describing here.
Yeah, that's kind of it. I fear that this is probably not the most clear description for people listening, but I think the key element is that Hinton is starting with the Hopfield network, so these things are related, and what he's adding to the Hopfield network is some randomness, so that it doesn't automatically settle into one of the local minima. And I
But
think
it's
it
believable randomness. That's why you gave the simulated annealing example.
right. It's believable randomness because it's sampling from a Boltzmann distribution. So I think initially he was mostly looking at things like optimization problems, and then he wrote some papers with a guy named Terry Sejnowski, who you know is kind of a local connection for us because he worked at the Salk Institute for many years.
Mm,
He was a computational neuroscientist,
yeah.
and also, as I understand it, he was a student of Hopfield's. So there's another connection there.
Okay.
So Hinton and Sejnowski wrote some papers on using the Boltzmann machine, basically developing a learning algorithm using the Boltzmann machine. At that point, using the Boltzmann machine as an actual, neural network, like we think of it now, as sort of a machine learning tool.
Could we stupidly say then a neural network is encoding a huge variety of states based on how many perceptrons you have, and when I'm asking it for prediction, I'm asking it for some sort of piece of the state that it has encoded, with a little bit of randomness thrown in for salt and pepper.
Um, that sort of works. As I understand the Boltzmann machine, what it's conceptually doing is so it's a generative model in the sense that what it's trying to do is it's trying to you give it a bunch of examples, and it's trying to create a statistical distribution that reflects the examples that you give it, the labeled
Hmm.
examples that you give it.
So maybe it's like recombining states that it has seen in the past, sort of.
Well, it's recombining them in the sense that it's building up the statistical distribution as it goes. And so later on, when you present it with new data, it can sort of say, does this reflect something that is within this statistical distribution?
Hmm.
So it can serve in that way as a classifier or a pattern matcher.
Okay. Okay. I think I'm kind of with you. If we go any farther, though, I think I'm going to have to really take a very long nap after this, and I need to go do some yard work.
All right, I'll wait for you.
I, I don't know. This conversation is interesting. There's a lot of heady ideas in here. I don't know how well we did trying to explain them. I'm pretty confused myself, to be honest. If you're confused listening, I'm confused describing and try to ask questions. I don't know if I'm really convinced that this is physics, though. Do you want to try to convince me this is physics?
I think it is physics in the sense that it has deep connections to statistical physics ideas.
Okay.
So I think they were recognizing two things with the Nobel Prize. One of which is that this does have connections. Both of these ideas, Hopfield networks and the Boltzmann machine, have connections to statistical physics. So they sort of arose from ideas in physics, and also that these are foundational things in machine learning, and so have contributed to the development of physics since
Hmm.
they were originated. It's different, certainly different than discovering a new particle in an accelerator or
Yeah, fair. Obviously, I'm just a guy off the street. They don't need to convince me that this is physics. I don't really understand this stuff anyway. So you could tell me that it's physics, and I'll be like, yeah, okay, I get it. But tell me this, Mike. Someday they award you the Nobel Prize in Literature for your work on the podcast, Picture Me Coding. If that happens to us, I will graciously accept. I'll certainly take the money. I'll put it on my resume, and then somewhere in my heart, I'll be a little pissed off about it.
Yeah, same. I think my concern would be probably a lot of people out there are thinking that giving Bob Dylan the Nobel Prize for Literature is kind of a low bar for the Nobel Prize, and my concern would be that people would think, oh, well, they've lowered the bar again. So
Even lower than Bob Dylan. All right, my friend. Thanks for explaining things to me this week. This could be a puzzler. And I think our homework is to go out and code up these things, right? That's our homework for the week.
I am going to attempt to still understand more about content addressable memory. Probably not everybody is susceptible to this, but I always find that when I see things that are similar but are in fairly different areas of thought, it
Mm-hmm.
it just obsesses me. And so that's
Kind of like a
probably
bagel sandwich. Is that a sandwich or is it a breakfast item?
no, not like
Oh,
that.
okay,
But
okay.
I'm kind of hungry now. But so for instance, I was reading what's his name? Avi Widgerson's book. And uh,
What's the name of the book?
it's called Mathematics and Computation.
Oh, wow, that sounds like a book I don't plan to read.
Yeah, it's pretty hairy. But anyway, I remember reading a part in there where he's talking about how random walks can be related to the Riemann hypothesis. And my immediate reaction was, I have no idea what that means, but I really need to understand that now. I'm not going to be able to sleep until I can understand that. So anyway, so I apologize to our listeners who were confused by this episode, but I get really excited when I see things that are the same but different.
Oh, I like it when you get excited. It feels like we're taking a random walk through the wilderness. You're going to take me along with you. I'll ask questions, and then I'll be like, oh, there's a dolphin. Nice. All right, my friend. Thanks for hanging out with me this week. This has been Picture Me Coding with Erik Aker and Mike Mull. Mike, I will see you again next week.
See you next time.
Bye-bye.
Bye.